Okay. Now, it's turned down. All right, so wrapping it around, you need the outside and inside radius, right? So the outside radius is distance from here to here. The inside is here to here. So the outside is going to be the distance from the x-axis to here, which is just the function, which is what? 2 over x. That's this one. But you have to add this distance, which is 2. So that should be 2 plus 2 over x. That's the outer one. The inner one is the bottom function from the x-axis to here is what? From here to here? That's the x minus 1 squared. But then you have to add 2. So you can write it different ways. X minus 1 squared plus 2, or you can put the 2 in front. That's your inner. And then you have to just go to the formula. And since you're using, what, washers, shells? What is this? Washers, right? Washers. Shells is the problem on the back. So you'll have pi integral 1 to 2. And then you'll have outer squared minus inner squared dx. So just take this right here, 2 plus 2 over x, square it, and then that, and that's all I wanted. That's it. Just plugged in. 2 plus 2 over x, and then x minus 1 squared plus 2. All right? Let me see where I am here. All right. The one on the back, did anyone do the one on the back? Tried it? Okay. The one on the back, I'm going to go really, really fast. You got that same region like this, same rectangle. You're rotating around this. So the integral is 2 pi, integral 1 to 2. And then you just got to know the radius, which is the distance from the axis of rotation to your rectangle. So the distance from here to here, I believe, was 3. Yeah, that was 3. And the distance from here to here is x. So here to here, which is your radius, is 3 minus x. And then it's the top function minus the bottom function dx. You're done. So top one is 2 plus, sorry, not 2 plus. It's just 2 over x goes here minus the x minus 1 squared goes there. All right, and dx. So that's what you should expect on your exam, okay, where I give you a region. Now, most likely, I will give you at least one where I give you the region, the picture like I did, and then ask you for a couple of rotations. Usually, I'll ask you for x-axis, y-axis, x equals a number, y equals a number. 4 rotations in one problem, and I'll probably ask you 2 or 3 problems. So the speed at which you get those formulas set up is important. That's why I wanted to give you this quiz, to give you an idea of what I would expect you could do in 8 minutes. I think this is maybe, I don't know, 12 would be tops that you should need for this. So I think we're not there as a class yet if we're not all getting this within that time frame. So you're going to have to work on the speed of things, all right? All right, well, it's just one quiz. Don't worry, I'm going to drop at least one. If we have 12, I'll drop 2. I think this was the 6th one. So I'll try and do weekly quizzes. They just eat up too much time. 15 minutes gone. All right, so this is what I want to start with today. And I'm facing this way because there's some stuff I want to show you that my internet students are going to need to see also. So see how this works, all right? I have no idea how the video quality is going to turn out here. Especially when I turn the projector on. I don't know if I'm going to get glare, if the brightness is going to wash the video out. I'm not sure. All right, we finished up last time. We were doing arc length, right? And I proved at the end of class that the circumference of a circle, right? I proved that. And there was a few of you that liked it. Nobody else did. So now what we're going to do is change our perspective. We're going to look at the same idea of taking a function. We're still going to wrap it around the x-axis, all right? So we're not going to take it off and measure how long it is. We're going to wrap it back around the x-axis like the good old days. But instead of looking at the volume of this, we want to know the surface area, right? That's what we want to know. And last class, we said that if we had a curve, we can measure its length by the integral a to b. Anyone remember? It's kind of ugly. Y prime squared dx. Remember that? And I showed you we had to pick the problems very special or else it wouldn't work out. Well, this problem, as we're about to see, the integral that we're going to get from this to get us that surface area is actually connected to this. And you'll see why. What have I done? What have I tried to instill in this class? Every time I've tried to set up a formula, I've always tried to back it up with geometry, right? I've always tried to show you a picture of where the formula comes from rather than just giving you the formula. So I'm going to do the same thing here. Imagine that we're going to take a little band off of this surface, right? If we could figure out what the area of that band was, then we could add them all up, right? And get the total surface area. So let me try and figure out where I could find the area of that red band from, all right? So where could I get that? Well, what I could do is I could almost imagine, again, taking a rectangle like this, right? And wrapping it around. But I'm only concerned about this top edge, right? That top edge is going to create the surface. Do you agree? The top edge of this creates the surface. The stuff on the inside would have created that inside piece. That would be the volume, and we already did that, right? I just want this outside edge. Are y'all with me? Y'all look stunned from that quiz. Are y'all all right? Okay, so let me take this red piece and just show it to you over here. The difference between this one and what I've drawn before is that this is more like a rubber band in the sense that it's just a real thin edge, right? Put my hand through there. So what is the area of that, right? What is the area of that? So I get out my scissors and I cut it, right? And I lay it open. And if I lay that open and turn it sideways, I get this big, long piece of tape, basically, right? And we know the area of a rectangle, don't we? It's just length times, in this case, the height. Yeah? So it seems like that's all I have to do is figure out how wide this is, figure out how long that is, and I'm done, right? But there's a little bit of a subtlety in here. I don't want to use a flat rectangle. I do not want to use just a straight edge across here. And the reason why is because this is a curve, right? It curves a little bit. What would be even better is if I were able to account for that little waviness here, right? That little waviness in there that I might get. And so this edge over here has the waviness of the curve in it, would be this edge, wouldn't it? Like that. And what is that right here? It's always been dx, hasn't it? It's always been dx because we've assumed it's just the width of that rectangle. But now I wanted to account for the curvature. It's the length of that piece, isn't it? It would be a better approximation if I used the length of the function right in there, wouldn't it? That's the way I'm going to do it. Instead of using just a solid straight line, I'm going to use the length of the curve right there. And, well, last class, we learned that the length of the curve is this, isn't it? So this piece right here is going to be the height of a rectangle. And then this piece is what? It's the circumference of this, right? Take this, imagine from here to here. If I cut that open and laid it out, it would be the circumference. We've done that before. The circumference is 2 pi r, isn't it? 2 pi r. So this should be 2 pi times the radius. But what's the radius? What is the distance from here to here? That's the height of the function, isn't it? That's how tall the function is there, which is f of x. I can call it f of x or I can call it y, can't I? Let's call it y. That is the area of that one red band going around the function. Then what I'll do is I'll move this thing back and forth, right? And I'll add them all up. And that gives me the surface area. So my formula then for surface area should be what? I'll leave the length formula up there. Should be what? This times this, right? Oh, sorry. This was dx. It's the formula for it, the entire thing. This. So it should be integral, right? What goes out front? 2 pi, because I have a constant right here. Also, let's call this SA for surface area. You could do S dot A dot. Surface area will be 2 pi and then y, right? Which is f of x, same thing as f of x. Square root of 1 plus y prime squared dx. That is the formula for the area of the surface generated by wrapping a function around the x-axis. Now we also need the limits of integration, right? A to b. A to b. A to b. I could replace in here, right? Y's could all be replaced with f of x's. This could be f prime of x, and it would be the same formula, wouldn't it? Okay, just keep that in mind. All right, that's it. Now, I'm not going to give you a lot of problems off of this. It's just more to expose you to it. Yes?
Just for clarification, your y came from your r?
Yes, my y is the radius.
Okay.
It's the function's height right here. This was f of x, which is the same as y, right?
Okay.
Why is there a dx at the end and not a dy?
You have to go back from last class and figure out where we got this from. This we got from doing a arc length and approximating it with the right triangle, calling this dx and calling this dy, and then using Pythagorean. And then we factored something out of the square root, and what popped out of the square root was the dx.
So are we going to replace anything?
Are you going to,
Replace the y?
with f of x? So like if, well, let me do an example, okay? So how about this? I had in mind today what I wanted to find the length of, the surface area of. I thought that you might like it. What do you think I was going to find the surface area of? A sphere. Exactly. Y'all interested in that? Okay. Would you like to find the surface area of a particular sphere, like with a certain radius, or do you want me to do a general sphere where we actually create the formula? You want the formula? All right, so you want me to create the formula? Okay, let's first look in the back of the book. What's the formula for the surface of a sphere? Someone gives you a sphere. What's the surface area according to the formula? Four pi r squared. Right? I beat you to it. So 4 pi r squared is the formula for the surface area of a sphere that has a radius of r, right? So how could I come up with that formula? Take a fourth of a circle, right, and wrap it around the x-axis. So take a circle of radius, what? Little r, right? R this way, r that way. A circle with radius little r, wrap it around the x-axis, and then double that answer, and it better be 4 pi r squared. Yes?
Is it just a coincidence that that's the derivative of volume of the sphere?
In some respects, yes. Yes, coincidence. Yeah, I'm trying to think of like beyond this if there's something like way out there that I've looked at before, but right now I don't believe it's connected. Like you can't arbitrarily take the volume of a solid, take its derivative and get the surface area. So it's more coincidental than anything else. Okay, so you ready? What do we need in order to do this then? What do we always need to get if we're going to, the equation, the function itself, right? I think we've done this enough. I hope we have. That this would be f of x is equal to the square root of r squared minus x squared. Remembering that r in the problem is a constant, right? The variable is x. So what are the things we're going to need for the surface area formula? We're going to need the derivative, right? And we're going to need to square it and add 1 and do all that junk that we did before. So I like to do all that on the side first. I like to actually figure out what's the derivative of f. Well, we did that last class too, didn't we? Or class before? I think it comes out to be negative x over square root r squared minus x squared. That's your derivative. Do y'all agree? Okay, and then we have to do what with that in the formula? Square it first, then add 1, right? So I need to square this. Notice I'm using f prime instead of y prime, right? So when we square it, we get this, right? And now I'm going to go and set up the formula. So the surface area should be 2 pi integral what to what? 0 to r. And then y, right, which is f of x, which is square root of r squared minus x squared, times the square root of 1 plus the derivative here, right, the derivative squared, which is this. That's it. That makes sense? That does not look like a fun integral, does it? Not yet. What did we do last time? We got a common denominator. We put these together. So what would we get if we put those together? I'm going to erase this. Two pi integral 0 to r square root r squared minus x squared times square root of, what do we get if we put these together? I put the 1, this together. R squared over r squared minus x squared, right? Dx. Yeah? That's exactly what we did last class at the very end. The only difference between what we're doing now and last class is this piece and 2 pi. That's the only difference, right? Now, last time what happened is that I took the square root of each one. The square root of r squared was r, and I popped it out. And what we had left was 1 over that root, didn't we? And then we actually used a formula right out of our book. We said we could have used trig sub. This time, it's even going to be better. Because, do y'all see what happens? If I do this, I take the square root of top and bottom, right? Separately. These two cancel completely. And all you're left with is what? Square root of r squared, which is just r. And can I pull that out of the integral? An r out? Yes, it's a constant. So I have 2 pi r integral 0 to r of what? 1 dx, right? Just 1 dx. What's the antiderivative of 1 with respect to x? X. So this is just 2 pi r x evaluated 0 to r. Right? Antiderivative of 1 is x. Now plug in r, what do you get? 2 pi r squared. Plug in 0, what do you get? 0. So this is our answer. but that was half of the sphere. So double that answer, and what do you get? 4 pi r squared. So that actually turns out to be an easier integral. I don't need any formulas at all. The main part of this demonstration is just really to show you that the only difference between surface area formula and arc length formula is the 2 pi out front and this additional f of x that'll be here. Sometimes that f of x will make this nicer. Sometimes the f of x out there will make it more complicated. So I want you in your book, why don't you try for homework. I didn't give anything off of this last time, right? Okay, so how about page 397? Maybe something like 5. That's very, very basic. Number 7. Number 11. Oh, whoa, whoa, whoa. Scratch 11. Scratch 11. Maybe 10. 5, 7, 10. That's good. That's it. Done with that section. All right? Just wanted to show you how it worked, right? I told you last class, I'm not really getting real deep into the arc length and surface area. Just want you to see it, all right? See it once. Now, there is another section in the book that I'm not going to cover at all, but I want to mention something from it. It's 7.6, which, if I have enough time in a class, I will cover 7.6. But in my history of teaching this class, anytime I try and get into 7.6, I always have to give up something at the end, and I'm not willing to give up the stuff at the end for this. This section is called applications. So I know for a lot of you, like, I wish, I want to see this working in the real world type thing, and I understand that completely, but that's the difference between a math class and an engineering class. And in the engineering class, that's where you can do the application. What you need to know how to do is do integration and do that. So hopefully you've got those tools. But let me just mention a couple of things that you can do with applications that this section talks about. One of them is, if you have from physics that work equals force times displacement, and later on that becomes a dot product, and it gets more complicated than just traditional multiplication. But work is the force applied on an object times the displacement. So if I drag a body across the room, it's Halloween, okay? So I'm dragging a body across the room, right? And so I'm applying a force on it over some distance. Then I multiply those two and I get the work that I've done in moving the body across the room, right? So if you have force here and displacement here, or the other way around, then the area underneath this comes from a bunch of these rectangles, right, that I put together here. And each one of them, the width is a force and the height is a displacement. And so the area of that is a force times a displacement. So that little sliver, the area of it, represents the work I did on that little infinitesimal slice. And so if I add up all the area, I get the total work done. I talked about this in the very beginning also, so maybe now it makes a little more sense. But these two variables, whatever they are, whatever they multiply to be, if that quantity has meaning, like in this sense it does, then the area is going to be something useful to us. Another application that's kind of interesting, I didn't bring, I can steal this. Let me see. Someone's going to get mad at me for this. All right. Nobody saw me do that.
It's on camera.
No, I was off camera.
Right.
This is the way I found it. So this is what we would consider to be, we call this a lamina. It's a sheet of paper, basically. All right? we call it a homogeneous lamina, meaning that we are assuming that whatever this is made out of, it's uniform throughout the entire surface. Now, we know that's not true because, the way I tore it, it's actually thinner over here than it is over here because I tore some of the inside out. Y'all see that? But let's assume that it was the same throughout. Then we call this a homogeneous lamina. And so if someone gives you a homogeneous lamina like this, we actually can use integration to find its center of mass, to figure out the point, wherever the point is, that represents the center of that mass. And what's the center of mass? It's basically the point that you could balance this. I think I tore it out, right? I think I did. I'll change it a little bit. I don't know. I don't think I'm going to be able to get this. I might have to cheat. There we go. Okay, so there's your center of mass. So the entire object balances on that center of mass point. And so with integration, we can find the center of mass. There's formula for it. You can look it up in the book, all right? It's just a simple, well, not as simple. It's just an integral, though. That's all it is, all right? Not only that, if later on in calculus, if this is a non-homogeneous lamina, meaning it does have variation in density throughout the object, you can still find the center of mass. But you have to account for that. So the integral becomes more complicated. And you'll do that like in Cal 3. You can do applications that way. So that's kind of cool. And especially like if the center of mass falls outside the object. Is it possible for the center of mass, something center of mass to be outside the object? Absolutely. Boomerang, right? A boomerang is an example of something where its center of mass is not on the object itself. A sphere, right? Take a sphere. Imagine it's a hollow ball. Where's the center of mass? It's in the inside, right? It's not on the surface. So centers of mass never have to be within the object itself. So, but we can find those centers of mass using integration. We can also find what are called moments of inertia, and that has to do with an object's resistance to rotation. So if I give you, let's see, this is kind of, what would be easier for me to do? Oh, shit. Would it be easier for me to spin this like this? I'm talking like how much force would it take for me to spin it like this versus if I turn it this way and try and spin it like this? Which one is going to require more force? What do you think? Are they the same? It depends on the object itself. It seems like the shorter one because your mass is closer to your axis of rotation, and the closer it is, the easier it is to turn. And so we can find that a number that represents that resistance to motion. That's what inertia is. Inertia is an object's tendency to want to stay in place, either moving, keep moving, or not. I remember my grandma was old school. She didn't want to wear a seatbelt. And I can remember my brother very distinctly. He told my grandma, put on your seatbelt. She's like, I don't believe in seatbelts. My brother said, you believe in inertia? And anyways, she didn't put on her seatbelt. But inertia, an object's going to want to stay in motion, right? So that rotation, right, is something we can compute using integrals. One more thing. Hydrostatic pressure. So you have a dam, right? You have a dam that's holding back water. If you want to calculate the pressure being applied at different points or the total pressure on the dam wall, you can do that using integration. And it's kind of a simple idea. It's hard to do generally. If this is a dam and you've got your water here like this, then what you do is you take like an infinitesimal layer like this and you try and compute like the force on at that infinitesimal layer, and then you add up all the infinitesimal layers. Something like that. All right. It all ties into cutting things up into little pieces and adding them up. Anything that requires that is where the integral is going to come in. All right. We good? Y'all ready to get out of chapter 7? Not really? You don't want to stay there, huh? I've been warning you about chapter 8. All right. We're still good. So here we go, chapter 8. There is a section, another section that we don't cover, 7.7, called Differential Equations. The reason we don't cover it is because you can take an entire semester course on differential equations. There's nothing I can say in 2 days that's going to give you any sort of good treatment of that topic, so we don't really cover it. Chapter 8, series. All right, we're going to start with 8.1, which are called sequences. There's a lot of definitions. There's a lot of theorems in this chapter. All right, yes?
This is going to be in third exam, right?
I don't know. We need to talk about third exam because I initially put third exam on the 12th of November so that anybody that thought they might want to drop the class could drop on the 13th. But if we have it on the 12th, man, your final is going to be loaded very heavy with chapter 8 because I don't think I'm going to get to maybe the third section at the most by the 12th, which means a lot of chapter 8 is going to be in the final. So I don't know. What do y'all think? Do y'all want to keep it at the 12th, or you want me to just kind of let it be flexible? You want to see some of this first and then tell me later?
Yeah.
Okay, all right, let's do that. I don't want to box you in, you know, I don't want you to paint yourself into a corner here. All right, sequences. So if we could, let me talk about what series are some of the applications before we even get started. That way you kind of have like a picture of why and where we're going. All right, so why do we do series? Series are used for a lot of things. Here are just a few examples. Signal processing. Signal processing. That has to do with, you know, you're running an experiment in a lab setting and you're collecting data, and that data you're trying to analyze. So signal processing is where series come into play. Differential equations. I'm just going to put diff EQ. Differential equations is the section I'm skipping in the book, or I'm not skipping, we're not covering because it's an entire semester course. To solve differential equations, you can use series. In computer science, CS, doing what's called numerical analysis. Anytime you have some sort of heat equations, which ties into the differential equations, but heat equations where you're trying to figure out heat transfer from one object to another, series come into play. All right, there's so many things that series are used for. I can't treat it properly. You know, I can't sit here and tell you every example. So if we could, can we get the projector on and the lights, all lights off, and please don't go to sleep. We're going to watch a movie. I brought in Frozen. I hope everyone's okay with that. Whoa. Here it comes. Here we go. I think I can see that. All right, so we've all seen the sine curve, haven't we? We've all seen the sine curve. So when you go and you get on your calculator, well, you shouldn't need a calculator for this. If I say, what is sine of pi over 4, everyone's like, sine of pi over 4 is root 2 over 2, right? Because that's one of the common angles. But if I say what's sine of just 4, then everyone breaks their calculator out, right? So what is your calculator actually doing to figure out what sine of 4 is? Is it sitting there going, well, I've got the sine curve, and I'm going to go out to 4, and I'm going to plug it in and figure out what the hell is your calculator doing? All it knows really is what? I mean, what can a computer do? At the end of the day, what can it do? What's the only thing computer knows? 1 and 0, right? On or off. There's either an electrical signal there or not there. That's a 1 or a 0. It's binary. That's it. That's all it can do. From that, you can get a computer to do basic operations: addition, subtraction, multiplication, division. Right? That's it. I mean, there's nothing more. There's nothing more to it. So when you type in sine of 4, what is the calculator doing to get an answer? Or if you type in sine of pi over 4, if you don't know your unit circle, and it spits out root 2 over 2, it'll usually spit out the decimal, right? So where's this coming from? So this is where series come into play. What I want you to see here is right now I have a red function graph. That's the traditional sine curve, right? Yes? And then I have a black curve graphed right now. You can't really see it because it's the x-axis. It's the function f of x equals 0. I have it right there. You see it? 0? F of x is 0 is this black line. Do you think that my function f of x equals 0 is a good approximation of a sine curve? No. That's a terrible approximation. You wouldn't say that those two are close to each other at all, would you? Not at all. So let me tweak it a little bit. Let me change it to, instead of 0, how about x? Is that better? It's a little bit better. I mean, for at least at 0, it's the same, right? Yay, right? Sine of 0, 0. If I plug 0 in there, I get 0. So at least at one point, I'm close, right? I'm exactly the right. And then it's kind of linear. All right, so let me change it a little more. Let me make it, instead of x, how about x minus x cubed over 6? So now it's a cubic polynomial. Is that a good approximation? Well, kind of, right? Kind of. It's looking kind of good in here. Out here, I start to fall apart a little bit, don't I? So how about I add some more to this? Make my function more complicated. How about that? It's a 5th degree polynomial. You see this? How's that? It got a little better in here, didn't it? Now I'm going to keep doing this. Uh-oh. What did you? Okay. Do you see them? Do you see them? Now I'm leaving the dotted ones. Those are the ones I'm leaving behind, okay? So you can see that the black curve is actually getting better and better, isn't it? Now I'm actually at a 17th degree polynomial, right? I have a 17th degree term in there. I've got a 15th degree, a 13th, an 11th, a 9th, a 7th, a 5th, a 3rd, and a 1st degree, right? Notice there's no evens in there. No even powers of x. They're all odds. If I were to continue this and continue building this, what would happen is I would actually be able to get a black function that gets closer and closer to being on top of the red function. And if I go forever following a certain pattern, because there is a pattern in this, the powers keep coming up by 2, right? These numbers, though, where are those coming from? Well, there's a formula for it. We'll see it comes from what's called Taylor's formula. And this is what we call later on a Taylor series. It's later on in the chapter. And so what we can do is we can take a function and we can model it with this Taylor series, and we can make our Taylor series as close as we ever want to be to the true function. And that's what your calculator is using to figure out what sine of 4 is. See, if you plug 4 into your calculator, what your calculator does is takes this polynomial and plugs 4 in. Why? Because your calculator can very easily do 4 cubed, right? 4 times 4 times 4. That it can do. It can do 4 to the 5th power very easily. 4 to the 7th, because the computer is fast, right? It can do arithmetic much faster than we can. And so what happens is these calculators have built-in algorithms where they go out. They don't go out. I mean, if we could go forever, it would be the red function, basically. We can't go forever. So the calculator stops at some preset, predetermined tolerance and spits out an answer. That's what it's using, though. It has no idea that sine is this wavy-looking thing. Has no clue. It looks at it as a power series. All right? And this goes for just about any function you can think of. Here's the function 1 over 1 minus x, the red one. Is my approximation good? 0? No? Okay. Is that better? 1 plus x? Better. 1 plus x squared, that okay? Do you see what's happening? Now notice that between about here and here, my black function is getting better and better, isn't it? But outside, this way, it's not doing good, is it? Okay, this is what we have in this case is we have a series of power functions. Notice my language there? A series of power functions, which is pretty darn close to the function I'm trying to approximate within some interval. And we call this interval where it's actually doing a good job, we call it the interval of convergence. And we will have to later on find out what that interval is. All right, we'll have to actually determine, like in this case, it would be from -1 to 1. And then if you want to figure out what's going out here, we will have a way of shifting our approximation over using what's called the Taylor series, and we just shift it about. So, yeah, huh? What's different between this series of power functions and the one before? It has evens and odds, doesn't it? Has evens and odds? Let's look at another one. E to the x, the exponential function. 1 plus x, 1 plus x squared over 2. Look at this one. Can you all see that? Look at that. It looks like even if it doesn't look like I'm going to run into that same problem I had on the last one. You know, on the last one, there was this point at which my approximation just sucked after that. It looks like the further I go out, I still keep on getting closer to the red function. So it turns out that for e to the x, this power series is always going to converge. So the interval of convergence actually is the entire number line. And so you could actually define e to the x to be this function. And that's what your calculator thinks it is. All right. This one, e to the negative x squared, looks like the red one. If I come up with the power series here, see, it's working, isn't it? I'm able to approximate it. I can keep going out forever. Looks like it's going to work. It's this right here. Now, why is that important? Because if I were to ask you right now to integrate e to the negative x squared, I mean, if I were to say, all right, everyone, quiz, what's the integral of e to the negative x squared dx? If I were to ask you to do that right now, nobody in this class would be able to do that. Nobody. And remember, there were two fathers of calculus. I don't know if y'all heard this back in Cal 1. The two fathers of calculus were who? Do y'all know? Newton and Leibniz. Isaac Newton and Leibniz. I don't know Leibniz's first name. Both created calculus independently of each other on different parts of the world. And then found out later they were doing the same thing. So if I ask you to integrate this, you wouldn't know how to do it, but guess what? Leibniz wouldn't know how to do it either. Newton would. Because Newton had power series. He had actually come up and was onto this. So watch, if I want to integrate e to the negative x squared, right? If I want to do it, if I can rewrite e to the negative x squared as its power series, could you integrate 1? Antiderivative 1? Yes. Can you integrate that? That? Yes? And so in order to integrate e to the negative x squared, even though there's no technique of integration to do it, if you first rewrite e to the negative x squared as its power series, you could integrate term by term, and you could get an answer as close to the true answer as you ever want it to be. So it's much more powerful with this series idea. I'm trying to sell you on the value of this. I don't know if I'm working here. How about here's sine of x cubed? See, even something like sine of x cubed, I can approximate it. What do you notice about the sine? The approximation of the sine, they're all what? 3, 9, 15, 21? they're all divisible by 3, but even less than that, they're all odd, right? And what about that cosine one? They were all what? Even. Hey, wasn't cosine an even function? I wonder if the word even has anything to do with that. It's exactly what it has to do with. That's where it comes from. The idea of an even function is that its power series involves even powers. An odd function, the power series involves odd powers. And if you mix them up, then it's neither even nor odd. So you didn't probably know that, but now you do. It's actually tied to this whole thing, power series. All right. One more thing. At some point, I'll probably offer this as like a bonus Fourier series. It's not in our book, but this is something that computer scientists deal with. Ruben, come on. Maybe like a lecture you can come into, like I'll offer you come in for an hour and we'll meet in a room and I'll go through this whole thing just to expose you to a Fourier series, but I can't take any time in class for it. This is what I want to show you. Remember I was talking about signal processing? So like you have this data where you're getting either signal or no signal, signal, no signal, something like that, and you have all this data and you want to somehow analyze it. You want to treat this as a function. But the problem with something like this is that we don't have functions that behave this way. This is like piecewise functions, isn't it? This is like a piecewise function. So I wonder if there's a way that we could approximate this with a nice continuous function. And that's what a Fourier series is. So I want you to see the Fourier series come in. Is that a good approximation of that? It's okay. Is that better? See, what this is it started out as a sine curve, but it's actually a sine curve combined with other sine curves and cosine curves that creates almost this drop-off table, like a table drop and then back up, this stepwise function. But it's continuous, because if you were to draw it, you'd be squiggling, like vibrating almost, right? And then you would go up and down, then you vibrate. So it's a nice continuous differentiable function as opposed to the original one, which had a bunch of breaks in it. So we can use that blue curve to approximate this, right? And so if you have something like someone singing and you're recording it, it's basically a bunch of waves. And if you can somehow model those waves with this, it's easier to compress that data. You get smaller file sizes and things like that. The compression of it's much nicer. So they use Fourier series for things like that, audio compression and blah, 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 blah. All right. Lights. I put too many people to sleep there. And can you turn the projector off? Thank you. That was just to try and sell you. I don't know if that worked. But. All right, here we go. So 8.1. Sequences. Let me zoom this back in. Did I hear someone go oof, oof, oof? Is that music I heard out there today? Did y'all hear that? My gosh. It was too loud. I went up to them and told them to turn it down. I was all the way over here and I could hear it. Was anyone in the science building when it was on?
Yeah.
Could you hear it?
Yes.
It's ridiculous. All right, I have 40 minutes. Let's see what I can do in 40 minutes. Sequences. So before we talk about series, we must first understand what a sequence is. Then, once we understand sequences, we can get into the series. So when you see the word sequence, what do you think of? Yeah. Sequence.
That's as good as mine gets.
Okay. All right.
That's all I got.
This is a list of ordered numbers. Now, in general, for those of you who might be going on to study math, like more of a pure math or computer science, a sequence does not have to be a sequence of numbers. You can have a sequence of functions or a sequence of whatever. All right? But in this class, for this chapter, we're going to look at it as a sequence of numbers for now. But it's ordered. So there's a pattern to it, or there's a first number followed by a second. If you switch those orders, it's no longer the same sequence. It's something different. So we like to write this list as follows. A set of braces to let you know that we have a list. It's A1, A2, A3. And then this list might stop somewhere, in which case I would call this A sub k. And this list would have k numbers, right, in it. And so we call this a finite sequence. Finite. Stops. As opposed to another type of sequence where we could have a list of numbers, A1, A2, A3. And then if I don't want it to ever stop, I usually use 3 dots. 1, 2, 3. That's the standard in mathematics, to use 3 dots to continue that pattern forever. But if you ever see me just go dot, 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 like, we all understand what I mean, right? I've never been real tied to the 3 dot thing. Sometimes it's 4, sometimes it's 8. It just depends on how much I want to emphasize it keeps going, all right? So this is going to be an infinite sequence. This was a finite sequence. Okay? Pretty standard, pretty basic, yes? No craziness yet? All right. Now, there's another way that I want you to view a sequence, and that's as a function. A sequence is also a function. Now, let me elaborate on this a little bit. We're all familiar with something like this, f of x equals x squared. That's a function, right? If I ask you to graph it, you would draw me a little parabola like that, wouldn't you? And the reason why you draw a parabola is because we have to have a way of representing every ordered pair, right? Like when I plug in 1, what does it spit out? 1. When I plug in 2, it spits out 4. When I plug in 3, it spits out 9. But there's all the other stuff too, right? When I plug in 1/2, spits something out. Everything in between. So that's what this curve is about. It's about trying to fill in the entire picture, isn't it? Yeah? Okay, so when we look at a function like this, we've kind of subconsciously agreed that x is a real number. X is an element of the real numbers. So that the x that you plug in here can come from anywhere in the real numbers, anywhere off that number line. Yeah? What if I now take that function and I restrict it? And instead of taking the function and saying it's a function of x, I say it's a function of n. And I define it to be n squared. And I tell you that n doesn't come from the real numbers. It comes from double-struck capital N. Now, what does double-struck capital N mean? You've probably never seen that before. Maybe you have. Anyone know? It's the natural numbers. This is the real numbers, the natural numbers. So what are the natural numbers? The natural numbers are the ones that you would think naturally occurred first. And that's 1, 2, 3, all the way forever. Those are the natural numbers. It's the set of all the counting numbers. 1, 2, 3, 4, 5. Yes? Not 0. 0 came later. 0 was a big deal when they figured it out. Like, oh yeah, we might need to use 0. If you believe in the history of progress of the way that thought happened, it was a lot of trading of things that our number system was needed for. So I don't walk up and be like, I'd like to trade, 0 goats. Zero just wasn't necessary until later. So 0 came afterwards. So those are our natural numbers. All right, so what if I restrict you there? Can you graph this? You're going to only be able to plug these numbers in, right? Which means that when you plug in 1, you get what? 1. And when you plug in 2, you get 4. And plug in 3, you get 9. And so, do I connect them? I don't, because that's all I'm allowed to plug in. So instead of it being a nice, smooth, continuous function, this is actually a function, but it's a bunch of dots as opposed to a nice, smooth curve. Do you see that? And it starts at 1 and goes forever, and there's just a bunch of dots going up. Now, do you agree that all those dots do lie on this parabola? It's just all the pieces in between aren't there. Yeah? And that's what a sequence is. See, we get away from this notation, and instead of writing down this, we say, no, because that's too confusing, you're going to think it's this. We write this instead. A sub n equals n squared. This is the notation that we use to define a sequence. I say, it's kind of like saying f of n. This is almost like saying f of n. But with the subscript notation, I'm telling you this is a sequence, and I'm telling you, by writing it this way, that the n is going to be from the natural numbers. Unless someone else tells you otherwise, you are to assume that n is always going to start at 1. Unless we say otherwise, which we will, but not yet. All right? So can you see that a sequence is a function? It just goes from the natural numbers into the real numbers instead of the real numbers into the real numbers. Yeah? All right, some alternate notations. We're just trying to get a bunch of preliminary stuff out of the way here, all right? If someone writes down a sub n equals n squared, I'm giving you, that's just one example. Another way they could write it is this. Okay, so this is one notation. This is another notation. They could even do something like this. What would that mean, do you think? Started at 3 instead of starting it at 1. So let me write next to this. What is this sequence? Tell me what this sequence is. What would I plug in first? 3. What's 3 squared? 9. What's next? 16, 25, so on forever, right? That's what that would be? As opposed to this, which would be what? 1, 4, 9. See the difference between those two? This one we assume starts at 1. This one, someone told us it starts at 3. How about this? Stop at 7. So this would be what sequence? 25. 36, 49. We're going to do n squared. We're going to start at 5. We're going to stop at 7. So that's 5 squared, 6 squared, 7 squared. Done. All right. No questions yet? Now, as we proceed through this chapter, there are some sequences that come up a lot. And we need to know how to generate these sequences on our own. So common sequences. Here we go. What if I want to create the sequence of natural numbers? My question to you is, what is the definition here of A sub n? What A sub n will generate that sequence of numbers? What do I need to define it to be? A sub n needs to be equal to what? N plus 1? What would n plus 1? Remember, we're going to start at 1, right? So if I plug 1 into this, I'll actually start at 2, and I don't want to start 2, right? I want to start at 1, so just n? That's it, right? If you define A sub n to be equal to n, you will generate the list of counting numbers, right? And we should always be able to generate that list. That's trivial almost, yeah? I'm getting a lot of looks like people are tired or... Look, you've got to pay attention. You've got to be ready for this, because if you're half awake in here right now, you're going to get blown out of here in a little while, all right? You need to like snap up, go outside, go up the stairs and down the stairs a couple of times, whatever. You got to get up, you got to be ready, all right? Because this is where I start to see a lot of people will fall off, okay? They look at this and they don't see it. It's because they're half awake. All right, how about this? So did anyone have a problem generating that sequence right there, up there? No one? Everyone understood the formula? Okay. This one doesn't come up as often as this one does, but there's something in this that I want you to recognize. Anyone see it? It's this sequence, right? Except everything's been shifted. So like they keep going up by 1, which is what this one does, right? It's just they start at a different place, don't they? Instead of starting at 1, I start at -2. And instead of 2, I'm at -1. And instead of 3. So each of these is 3 behind that one up there, isn't it? So why don't we just use that sequence and take 3 away? A sub n equals n minus 3. We're done. Do y'all see it? Okay, who said that? Someone said n minus 3. Who said? You're out. You're no longer, you can't answer any of the others yet. All right? Should what? Okay, I'll let y'all have one more shot. Then after that, whoever says it, all right? How about this one? 2, 4, 6. 2n? 2n. Yeah, y'all see it? It's just, those are all even numbers. Yeah, try 2 times 1, 2n. 2 times 1 would be 2, and then 2 times 2 would be 4, and then 6, and then 8. Y'all see it? Now these are the even numbers. All right, so put a little star next to that. That's how you generate the even numbers, 2n. I know this kind of still seems a little bit like, okay, where is it going to get hard? Just bear with me. Doesn't have to be hard, just, how about this? -8, -6, -4, -2, 0. All right, so who said 2n? You're out. Get out. No, I mean you're out. What is this? Yeah, go ahead. 2n minus 10. So you're seeing it's the even numbers. You're just shifting everything back 10, right? Yes? So 2n a sub n equals 2n minus 10. And you can always check it by just plugging 1 in first. You plug in 1, you should get negative 8. You plug in 2. 2 times 2 is 4, minus 10 is negative 6. But see, it's more important to see it that way. Even numbers, moving everything over by 10. You've got this down. Y'all are ready. One, 3, 5, 7, 9. Okay, if you've answered, you can't answer. Can't answer, Ron.
You say n plus 2?
Say what? Okay. Anyone? 2n minus 1? So how are you seeing that? I'm just curious. I'm just trying to figure out what you're thinking.
Well, I just plugged in 1 and then subtracted 1.
But where did you get the formula 2n minus 1 from?
I just plugged it in.
And this is what's hard about this now, okay? It's because I can't teach someone how to see that. And that's how the rest of this chapter is going to go. I can't teach you to see something that you either see or don't see. Right? Now, I can try and give you some more of a systematic approach. Isn't this all the even numbers minus 1? Isn't 1 2 minus 1? And isn't 3 4 minus 1? And isn't 5 6 minus 1? So aren't all the odds just the evens shifted over 1? So that's one way you could kind of visualize it, maybe. 2n minus 1, right? Okay. What about this? Two n plus 1. That's all the even numbers again, but this time shifted the other way. Instead of 2, it's 3. Instead of 4, it's 5. Instead of 6, it's 7. So it's up by 1 instead of down by 1. So 2n plus 1. Okay, we're getting fewer and people can answer now. That's kind of bad because the harder ones you're going to leave. Very important one right here. How are you going to generate that? If you answered, you're out. Anybody? You're getting there, getting warm. 1 to anything should be itself, should be 1, right? 1 raised to any power should be 1, so you can't use 1.
Is it the original one you just said, minus 1?
What?
No, never mind.
Like negative 1?
There you go. Did you say negative the first time? I didn't hear negative. You said 1. Negative 1, that whole thing to the n. Does that work? So if you plug in 1, you get negative 1 to the first power, which would be just itself. If you plug in 2 for n, you get negative 1 squared. Negative 1 times negative 1, positive 1. Negative 1, now you plug in 3, right? You get negative 1. Every even power is going to be positive. Every odd power is going to be negative. And so this will generate this, won't it? This is a very standard sequence. We call this an alternating sequence. You see why? Alternate signs. So this is the first example of an alternating sequence. Just out of curiosity, would this have worked? Yes? Yes, because what would happen if I plugged in 1 is that I would start with what? 3, and that would still be starting a negative, right? And then the next number would be what? After 3 would be 4. That's even. And then 5. So I could have done that, or I could have done, well, could I have done this? Would that have worked also? In fact, n plus what? Any even would have worked, right? N plus any even number, and I would have still generated that same sequence. Just wanted to point that out. Now, what about this one? 1, negative 1, 1, negative 1.
Negative 1 to the n plus 1.
Negative 1 to the n plus 1. Will that work? If you plug 1 in here, what do you start with? 2, and that's going to give you a positive 1. I've got to sneeze. Excuse me. Try to cover the mic there. Yeah, so that should work. If you plug in 1, you get negative 1 to the 2, which would be 1. And then from there on out, it would be alternating, wouldn't it? You could do any odd number up there, couldn't you? N plus any odd number, and it would still work. As long as n starts with what? 1. All right. Last one. Okay. This looks good. Okay. This is more like the stuff we need to be able to handle right here. Because that looks pretty complicated. You can start going, okay, 2/5 and negative 4/25, and start to try and find like some relationship between that number and that number. The way I like to look at these is just break it all apart. Okay, first, it's an alternating sequence, right? It starts positive, then negative, then positive, and I'm assuming negative, right? How do I create an alternating sequence that starts with positive 1, with a positive number? Negative 1 to the n or n plus 1. Does everyone agree that that will start me with a positive? And on the next one, I would get a negative, and then positive, and then negative. So that should create the sign change I need, shouldn't it? Now let's look at the fraction. What's happening in the numerator? 2, 4, 6, 8. So the numerator are just the even numbers, right? Starting at 2. So 2n up there. The denominator, hold on. Ron, come on.
Yeah, 2 and then the bottom is 5n.
5 to the n. To the n? Or 5n?
To the n.
To the n. So 5 raised to the n. They're all powers of 5 down there, aren't they? 5 to the first power, 5 squared, 5 cubed. And so that takes care of everything, right? That should create the alternating we need. The numerator should come out right. The denominator should come out. You could do certain things to this, like you could move this up here, but that's it. I mean, that formula will generate that sequence. Now, the formula for a sequence is not unique. Someone could probably come up with another formula that's just this tweaked up a little bit, and we would get the same sequence. So don't ever believe that, your answer has to match the back of the book all the time, because you can be off a little bit. I mean, as long as you can simplify yours into theirs or theirs into yours, then you're good. Always just check it. Plug in one, make sure you get the first one. Plug in two, make sure you get the next one, so on and so forth. All right, now every sequence I've shown you so far, either I've given you the definition and we wrote out the sequence, or I gave you the sequence and you came up with the definition. There are some other types of sequences out there called recursive sequences. And there's a very famous one that you may be familiar with. I'll write it out first. Or maybe a little more. Anybody recognize that sequence? The Fibonacci sequence. Fibonacci, named after an Italian mathematician. So what is the pattern in the Fibonacci sequence? 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. So how do I get the next guy out here? What do? I add up the previous two. Right? How did I get 21? I added 13 to 8. How did I get 13? I added 8 and 5. How did I get 8? 5 and 3. So the next number out there should be what? 30 what? 4? That's the Fibonacci sequence. The thing about the Fibonacci sequence is there is not an easy formula for it. There's not an easy one. But there is a way that you can do it using what's called the recursive definition. And here's how it goes. What we know is that the first guy in the sequence has to be 1. We also know the second guy, oh, that's a girl, sorry. The guy is 1, the girl is 1 also. Okay, the second, I'm trying to be, politically correct here. The first two are 1, right? After that, do you need anything else? You just need to know what to do with those, right? What do you do with those? To get the third one, you add those up. To get the fourth one, you add the previous 2 up. To get the fifth one, previous 2, right? So what I know is this. If I want to figure out the nth one, all I have to do is take what? The 1 in front of that, which would be n minus 1, and add it to the one before that one, which would be what? A sub n minus 2. And that I would do for any n greater than or equal to 3. See if that makes sense to you. So I define the first two, right? Here they are, 1 and 1. Now, every one after that is the sum of the previous 2. So if you want to know what the nth one is, you add the n minus 1 one to the n minus 2 one. So if you look at these, it's a little easier if you look at these like maybe these are dominoes. Here are my dominoes. If I'm trying to figure out, whoa, that domino's all messed up. If I'm trying to figure out what the a to the n domino is, right? I have to look at the one before it and the one before that and add those two together. This is an minus 2, this is an minus 1. Take these two and add them up, and that will give me that third one, right? So this is a general formula, but it only works when you're looking at the third domino and out, because the first two are already defined, aren't they? That's what we call a recursive definition, a recursive sequence. Fibonacci sequence is when these are 1 and this is defined this way. If you change this to a 3 it's no longer Fibonacci sequence. If you change this to a 4 and left this back here as a 1, it's no longer Fibonacci sequence. Fibonacci sequence is a specific example of a recursive definition. It's not the only one out there. It's just a specific one. Yes?
So if you plug in 3 for both ends on your A sub ends?
And like 3 here for your first ones.
Over there, yes.
If you plug in 3
Yes.
right here,
Or, yeah.
then this would become, well, let's do it. A sub 3 would be A sub 3 minus 1, 2 plus A sub 3 minus 2, 1. So the third domino is equal to the sum of the previous 2. So, yeah? Okay. I'm not sure if you had a question. Was that a question or?
It's just making sure that that works.
Yes. But see, 2 wouldn't work, right?
Because you would go back to
You would go back too far. You don't know what A sub 0 is because it was never defined. Now there's some really interesting properties of the Fibonacci numbers, the golden spiral and all that stuff, and I could draw it on the board, but you can also use YouTube also to look up things like that. So if you're interested in the Fibonacci numbers, go look it up. All right, now there's one more thing I'll talk about today in the last few minutes, and that'll set us up for next class to get into the heavier stuff. This thing. What is that? Y'all seen that before? N, damn it. Right? And factorial. This is what we call the factorial. And the factorial is just a very short way of writing something out that could be very hard to write out. If you write down 5 with an exclamation point, you mean 5 times 4 times 3 times 2 times 1. You don't need the 1 there, but I just put it for illustration. All it is you take the integer 5 and you multiply it times the next number down, 4 times the next number down, 3 times the next number down, 2, then times 1. And whatever that number is. What is that number? 120? And that is the definition of factorial. Now, written in a more general sense, if you write down n factorial, then it should be n times what? 1 less than that, right? So couldn't I write that like this? N minus 1 times, and then 1 less than that one, which I could write as what? N minus 2. And I keep doing that, dot, 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 until I get to where? How about just 1? How about just 1? When we get to 1, we stop, right? That's the definition of n factorial for n element of, I can't use natural numbers though. What's the double struct z? Uh-oh. So double struct r is all the real numbers. We were familiar with that. Double struct n was the natural numbers, 1, 2, 3, 4, 5, 6. Z, double struct z, are the integers. That's 1, 2, 3, 4, 5 forever. It's negative 1, 2, 3, 4, 5 forever, and 0. Right? So this is 0, 1, negative 1, 2, negative 2, both directions forever. No fractions. If you want the fractions, double struct q. Now that's even more, but it's not everything. Double struct q is not double struct r, because there are things that are in r that are not in q, like pi, like the square root of 2. So this is all the fractions. If you put the fractions and the irrational numbers together, you get r. What about what? That's not, oh, what is it?
No, like where would it fall?
You know what? I don't know. I think it's irrational, but I could be wrong. Because it's the golden ratio, right? The golden ratio is not a fraction. If it was, everyone would know what it was. It's something that gets approached in a limit. We never get there, so I'm pretty sure it's irrational. So it would be in here, but not in here. I'll double check that, and I'll let you know. So what am I saying here? N factorial is this, as long as what? N comes from the integers that are greater than or equal to 0. That means these guys over here. So it's the natural numbers, isn't it? It's the natural numbers, but 0 also, right? So that means I can actually find out what 1 factorial is. Yes? What's 1 factorial? 1, okay. 2 factorial, 2 times 1. 3 factorial, 3 times 2 times 1. But according to this, I can also do what? 0 factorial. And so what is 0 factorial? It's 1. Why? We define 0 factorial to be 1. There's a video that you can watch on YouTube. The channel, I believe, is called Number File. I think I showed you with the encryption thing in the very beginning of class. Remember that encryption thing? The very beginning? We didn't do the encryption thing? No? Okay. I thought we did. Number File is a really cool channel if you like numbers. And math. And computer science. Number File. And they have a video on trying to explain why 0 factorial is 1. But for us, we're just going to take it on, we're just going to believe it. It's the definition of 0 factorial is 1. I don't think I have enough time to get into some of the properties of this. Would it make any sense to try and do this? 1/2 factorial. According to the definition, I shouldn't be able to. But there is, and it's a more complicated function we're not going to get into. Number File, they do talk about that, so they get into it pretty deep. What's your homework? Have fun. Have a good Halloween. I do want you to do that surface area homework. There's 3 problems. Make sure you're caught up on the arc length stuff. From the looks of the quizzes, then work on this volumes. Make sure you go back and touch on that. Yes? Okay. You're free to go. I'm just going to put this on video. You're not going to hurt my feelings if you leave. This is the Fibonacci golden spiral. So that's a square that has length 1, length 1. So that 1 is not the area, it's the measurement of each side. Remember the Fibonacci numbers are this. So if I draw another square next to this, it also has length 1. Because this side is the same, so it's 1 by 1. If I draw this square, that would be 2 and 2, so this would be 2. And then if I draw this square, it's 2 and 1, so this would be a 3. If I draw this square, this would be 3 and 1, so that's 5. If I draw this square, that'd be 5 and 1 and 2, that'd be 8. This square would be 8 and 2 and 3, so that would be 13. And then I'm going to go off the board. So if you start out in the first square, the first corner here, and you connect an arc swinging to the opposite corner, and then from that to the opposite corner, 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 you create the golden spiral. And that's the thing that they talk all about, golden spiral. Yeah. That's supposed to appear in nature all over the place and things like that. I've heard different things. I've heard stories supporting that and stories that say it's not true. But either way, that's the golden spiral.
Cool.